Good morning, I'm Manuel Zarzo, and today we will continue with the Unit 5 Inference Distributions in Sampling. This video today is about distribution of the sample mean. Well, imagine that this is the population where we have a property that follows some kind of distribution where we have an average that is m and the variance. Okay, so imagine that m and variance are unknown constants from the population. Then we can take a lot of different samples. SRS means simple random sampling, so we take a first sample of size n, another sample of size n, and so on, a lot of samples. And from every one of them, we compute the sample mean and the sample variance. Okay, from every sample, we compute the mean and the variance. So this would be the population of all possible samples that we can take. Good. And then imagine that the characteristic that I'm measuring is skewed. Okay, something like that. Okay, but what happens is that if I compute the average tends to follow a normal distribution. This is because of the central limit theorem. The average is sum of random variables divided by n. Okay, and always that I sum random variables according to the central limit theorem. This sum tends to be normal if this amount of variables that I'm summing is large enough. Okay, but if the sample size increases, then the variability will decrease. Okay, so the sample mean is calculated like that. So we sum the values measured in the sample divided by n, which is quite a simple formula. Each one of these values that constitutes the sample will be the observed value of a random variable that has an average m and the variance sigma squared. Okay, so we can compute the mathematical expectation of the sample mean, like the mathematical expectation of this. Okay, so by applying properties of the expectation, we finally get the value m, which makes a lot of sense. So the average of the sample mean is the population mean. Okay, I think that this rule makes a lot of sense, but this is true for any kind of distribution. It doesn't matter if this is skewed, symmetric, or normal. Okay, for any kind of distribution, we will have this rule. Then, what happens with the variance? The variance of the sample mean, okay, is this. So, assuming that they are independent, which yes, we can assume that because they are just values taken at random, we have this. So the coefficient goes squared, and then at the end, what we have is sigma squared divided by n. So we have this important formula. The variance of the sample mean is sigma squared, which is the variance of the population divided by the sample size. Okay, the population variance divided by the sample size. And this is true for any kind of distribution, because in these formulas, we're not assuming any distribution. Good. So, the sample mean is a sum of independent random variables with the same distribution. So finally, we have this, that if n is large enough, okay, if n tends to infinite, although in practice it's not necessary to be excessively large, according to the central limit theorem, we will have that the sample mean will tend to be normal. Okay, will tend to be normal. So this normality depends on the sample size. If the distribution is not normal and the sample size is small, probably it's not normal. But if the sample size is large enough, it will tend to be normal. The average will be m, and the standard deviation will be sigma divided by the square root of n. Good. So as I was saying, if I'm measuring values that follow a skewed distribution, okay, the sample average will tend to be normal, something like this, and if the sample size increases, so this probability of the sample mean will tend to be lower. Good. So in summary, so we have that if I have values, if I have random variables normally distributed with an average m and the standard deviation sigma, then what happens? What happens is that for any kind of sample size, so for any kind of n, so the sum will always be normal, and then consequently for any value of the sample size, the sample mean will be normal. So the issue is that if the distribution is not normal, okay, so we will require a large sample size so to get this to be normal. But if we are measuring a characteristic from a normal population, for any value of the sample size, the sample mean will tend to be normal. Okay, then we can standardize this formula, and then we have that the sample mean minus the population mean divided by this, divided by sigma, divided by the square root of n will follow a standard normal distribution. Okay, so in summary, if the variable is not normal, okay, so only when the sample size is big enough, it will tend to be normal. For example, if x is an exponential, for example, if just with 3 values, it will not be normal. So now we're going to apply these formulas in an exercise. Imagine that we have a process of car painting, and then we measure the thickness of the paint layer, and then let's assume that it follows a normal distribution with an average of 100 microns and with a standard deviation of 5 microns. Okay, so thickness is our quality parameter that we measure. We assume normality, m equal 100, sigma equal 5. Okay, then the quality control of this process is conducted by obtaining 4 values. Okay, so we take a sample of 4 values, okay, by measuring the thickness of 4 cars randomly selected. Then, once we have this sample with 4 values, then we compute the mean, the sample mean with n equal 4. Okay, we sum the 4 values and then we divide by 4. So the process is considered as correct if this mean is bigger than 95. What is the probability to regard the process as not correct? Well, that can be an exercise that we can propose, like when we have class exercises. So this is the application of the formulas that I have shown you in the previous slides. So the mean of the 4 measurements, okay, the sample mean will tend to be will follow normal distribution because the population is normal. Okay, based on this, that implies that the sample mean will always be normal. The average will be 100, and the standard deviation is the sigma, okay, the standard deviation of the population divided by the square root of 4, which is the square root of the sample size. Okay, so we have this is the distribution of the sample mean. So the probability of not being correct is equal that the probability of the sample mean is less than 25. So we standardize, and then we look this value in the normal table, and then we have finally the probability of about 2.3%. Okay, well, this is another exercise of application of these formulas. So in order to know the average expenses of Spanish families in summer holidays, okay, that is the parameter in the population that we want to estimate. So we take a sample of n families, okay, n families randomly chosen, and then we ask them about their expenses in summer holidays. The population standard deviation is assumed to be sigma equal to 100 euros. Well, actually, this is like a theoretical problem because obviously it's very difficult to have in advance this real about the sigma in the population. But anyway, so let's assume that we have that information. So calculate the sample size so that the difference in absolute value, because between the sample mean and the population mean, has to be less than 50 euros with 95% probability. Okay. Maybe the most difficult part in this exercise is to really understand this last sentence, and then that is better to make like a picture with that. Okay, so this is the distribution of the sample mean. Okay, the average is the real value of the population mean. Okay, so it follows a normal distribution. So we have a probability of 95%. So we get the interval so that inside we have 95% of the probability, so that on the left we will have 2.5% and on the right side we will have also 2.5%. Okay, Then it says that the difference in absolute value means that it can be on the right side or on the left side. It has to be less than 50 euros, okay? Less than 50 euros. So it means that this interval is less than 50. So if this is m plus 50, and then this is m minus 50. Then, so it's very important that you understand that from this sentence we have to make this kind of picture that clarifies a lot the problem. Well, now the issue is this, no? The probability that the sample mean minus the population mean has to be less than 50 in absolute value, with a probability higher than 95%. Okay? It's the same that's saying that the probability of the sample mean to be less than this value, less than m minus 50, has to be less or equal than 0.025. Okay? So we standardize the probability that the standard normal distribution has to be less than this value. Okay, so we make this operation, okay, because the distribution of the sample mean is the population mean divided with a standard deviation which is 200 divided by the square root of m. Okay, this is the standard deviation of the sample mean. Okay, and then here what we have is that m is simplified. Okay, so m goes out, and then finally we have to look at this table, at this value in the normal table, and then this is equal to minus 1.96. So as I was saying, the value m is simplified, and then we just have to solve, and then here we compute that n is equal to 62.1. Obviously, as n is the number of families, we cannot have 62.1, so we round up this value to 63 families, and that will be the solution of this exercise. And then here I finish this video about distribution of the sample mean.